Welcome to more density problems. So the density of silver is 10.49 grams per centimeter cube. If a sample of pure silver has a volume of 12.993 centimeters cubed, what's the mass? Okay, so here we already know the density. We're looking for the mass, right? And you can remember the formula we had from the previous page, or you can just set up the density equation. So density equals mass divided by volume. Right? And so here we know the density. It's 10.49, kind of going downhill here, grams per centimeter cubed. And we know the volume. That's 12.993 centimeters cubed. So the density and the mass is what we're looking for. So this would be 10.49 grams per centimeter cubed equals mass we don't know, divided by the volume, which is 12.993 centimeters cubed. Now to solve, we'll just multiply both sides by 12.99 centimeters cubed. Times 10.49 grams per centimeters cubed equals mass divided by 12.993 centimeters cubed times 12.993 centimeters cubed. All right, so this will cancel. All right, and then the units will cancel, right, because one's in the numerator, one's in the denominator. All right, and then all we have to do then is multiply 12.9993 times 10.49 grams, and that'll give us the mass. So now I'm just going to plug that into a calculator. 12.99. Oops, somehow I got too many nines in there. And it occurred right over here. Just two nines. All right, so 12.993 times 10.49 gives us 136.29657 grams. And there we go. All right, so whether you remember the formulas we had on the other page, or simply set up the density equation and solve for the missing one, you'll get the exact same answer. Right? So this one is done. So now you know how big a piece of gold there is, or excuse me, silver there is. All right? So sometimes that's used if you can't weigh the silver, right? But you know its volume. And you can find volume by just just putting it in water and seeing how much water is displaced. And the density, that would just be a common number, right, in a list of densities of different minerals. Then you could find out how much gold you have, or excuse me, silver. I keep wanting to make it more valuable. All right, let's try the next one. All right, so calculate the density of the rectangular pyramid below that weighs 936 grams. So first, let's find the volume. All right, so the formula for volume of a pyramid is 1/3 the area of the base times the height. All right, so the base is the rectangle there. So that's 13 times 6. My 13 looks like a B. So the base is going to be, so that would be 60 plus 18, so that's going to be 78 centimeters cubed. The height of the pyramid is 14 centimeters, It is the distance from the base to the vertex. So the volume is going to be 1/3 times 78 times 14. 78 is divisible by 3, because 7 plus 8 is 15, and 15 is divisible by 3. So 3 divided by 7, that would go in twice. It'd be 1 left over, so 26 times 14 means the volume is 364 centimeters cubed. All right, so now we have the volume. Now we can find the density. So density of the pyramid. And as a reminder, I'll just put the formula here for density. I think I need a little bit more space. So density is mass divided by volume. All right, so the density of the pyramid is 936 grams divided by 364 centimeters cubed, and that would be 2.5714. We'll go 4 decimal places out, and it wouldn't round up, so 2.5714 grams per centimeter cubed. And there we go. All right, so here we're combining what we learned in the previous lesson, volume, right, and using that to find density, our current lesson. Let's do another one. Water has a density of approximately 1 gram per centimeter cubed. A cylinder with a radius of 1 centimeter, a height of 4 centimeters, and a mass of 20 grams is placed in a swimming pool with water. Will it sink or float? All right, so first of all, let's find the volume of the cylinder. Right, so if this were something you'd want to, use to hold something in and want it to be able to, travel across water, you would not want it to sink. All right, but let's find the volume of the cylinder first, because we won't be able to answer this question without that. As a reminder, volume of a cylinder is pi r squared times the height. The radius is 1 centimeter, and the height of the cylinder is 4 centimeters. So that means the volume is pi times 1 squared times 4. Well, 1 squared is 1, and 1 times 4 is 4. So the volume is 4 pi. We're given the mass. Oh, and let's put the units there. Centimeters cubed. The mass is 20 grams. So now let's find the density. So the density of the cylinder is the, and I'll just put the little formula over here. So just as a reminder, density equals the mass divided by the volume. So that would be 20 grams divided by 4 pi centimeters cubed. Now, it would be fine to make that 5 over pi, but we're trying to figure out if it'll sink or float. So we better reduce this to a decimal. Right? So I'm going to take 20 and divide that by 4 pi. And if you're dividing by a number like 4 pi, make sure you put 4 pi in the parentheses. Otherwise, your calculator will divide by 4 and then multiply by pi, which is not what you intended to do. There we go. And I get 1.5915 grams per centimeter cubed. Not a single one of these is rounded up. The next digit has been a number that is less than 5. All right, so now will it sink or will it float? All right, so since the density of the cylinder, and as a reminder, that was 1.5915 grams per centimeter cube, is greater than the density of water, which is given to us right there, 1 gram per centimeter cubed. The cylinder will sink. The density would have to be less than 1 for it to float. So, will not float, it will sink. Right? So, we have solved another problem. Lots of good real-world examples here, problems for us to solve in this lesson. All right, so we want to find the density of a rectangular prism measuring 4 centimeters by 3 centimeters by 4 centimeters by 6 centimeters and weighing 7.9 kilograms. So I have it pictured there for us. All right, so there's length and width, or you can call it base and height. But as a reminder, the volume of the prism there is the area of the base times the height. So let's find each of those things. The area of the base, right, is, we just got to take the two base measurements. So 3 times 4, which is 12 centimeters squared. The height is just the distance between the two bases, the top and the bottom. Right, so the height is 6 centimeters. And so to find the volume, we just take the area of the base, which is 12, times the height, which is 6. So the volume of the rectangular prism is 72 centimeters cubed. Right, not too difficult. Now let's find the density. Right, so as a reminder, density is mass divided by volume. We're given the mass is 7.9 kilograms. So that means that the density of the prism will be 7.9 divided by 72, which is 0.10972. And that is kilogram. I forgot to put the units in there. This is kilograms, and this was centimeters cubed. There we go. And you might think, oh, this one would float because that's less than 1. But the water was in grams. Right? So 1 gram per centimeter cubed, is the density of water. Well, kilograms is a much heavier measurement than is grams. This one would still sink. Right. Let's try another one. I think we've only got a few left. You gotta love that picture. That is the irregularly shaped stone. Is that not beautiful? All right, so an irregularly shaped stone was lowered into a graduated cylinder holding a volume of water equal to 20.0 or 20 milliliters. The height of the water rose to 30.2 milliliters. If the mass of the stone was 25 grams, what was its density? All right, so let's find all the parts we need. So as a reminder, that density is the mass divided by the volume. All right, so let's find all the parts because we're looking for density. So that we don't know yet. So density is, mass is, so we're looking for the weight. There we go. The mass of the stone is 25 grams. Doesn't matter if you put the 0.0 in. All right, and then we need the volume. All right, so if it's already, so the volume is equal to the change in height of the water. Or you can think of that as how much water is displaced. So here's where you can't just plug numbers in blindly. You got to think how much water is displaced. Which of those numbers represents water being displaced? Well, the 20, that's the water that was already in there, right? That's our starting value. The height of the water rose to 30.2. That's the ending value. So the volume is the change in the height of the water, right? Or the how much water is displaced. So the amount of water displaced equals the ending amount minus the starting amount. So in other words, let me write that over here. I've got a whole lot of equals in this sentence. All right, so the ending amount is 30.2 minus the starting amount, which is 20. All right, and so that's going to be 10.2 milliliters. All right, so that's the volume. All right, so now that we have the amounts, so it wasn't really a lot of work. We just had to be able to identify the right values. Right, so the density of the stone, the mass is 25, the volume is 10.2, and so that would be 2.451. I'm going to round up. 2.451. It was, on the calculator, it was 0.9. So, and then it was 0.98. So we'll make that 2.451. And then it is grams per, now you can either make it grams per milliliter, or since this is a solid, and we don't usually think of milliliters, milliliters is a unit of measure for solids, we could also put grams per centimeter cubed. All right, so either of those is fine for the density of the stone. And the stone would also sink as well. That's considerably greater density than water there. Okay. All right, so when you've got irregularly shaped objects, we're not going to be able to find the volume using a formula from geometry. Instead, we're going to have to look at how much water is displaced. All right, so now let's try another problem. I think I might just have a couple problems with population density. I have one, I think I have 2, 3 after that. Yep, I have 3 problems altogether. All right, so let's finish up the last 3. I won't start a new video. A 200-gram steel ball is submerged in a rectangular prism with a base of 4 centimeters by 8 centimeters. The water rises by 1.25 centimeters. What is the density of the steel ball? All right, so these are some challenge problems here. All right, so first of all, remember that density equals the mass divided by the volume. All right, so now we're looking for the density, right? What is the density? All right, so we define mass and volume, right? Define that. All right, so mass is just the weight. It's a 200-gram steel ball. So 200 grams is the mass of the ball. The volume. So now this one is a little tricky. Again, we're placing it in some water, right? So, but we're placing it in a very specific container, right? So our volume is the water that's in the rectangular prism with a base of 4 centimeters by 8 centimeters and a height of 1.25 centimeters, because that's how much the water rises. So the volume for the steel ball, right, is going to be the area of the base of the prism container times the height of the prism container. And that height is the amount the water rises. So once you know what values you need to calculate the information, then it's not so hard. So let's calculate the area of the base first. So the area of the base is 4 centimeters by 8 centimeters. Right? So, and actually let's write that out, what we're calculating out. So we're calculating base times height, right? The two measurements that are in the rectangular prism that we're submerging the ball into. So the area of the base is 4 times 8, or 32 centimeters squared. The height of the prism is the amount the water rises, so 1.25 centimeters. And again, I'll just put amount water rises. All right, so the density is the mass, which is 200 grams, divided by, oops, we never finished finding the volume, sorry. We wrote down the things we needed, but never multiplied out the 32 times 1.25. So the volume of the steel ball is 40 centimeters cubed. So that makes the density 200 grams divided by 40 centimeters cubed. This one's pretty easy to figure out. That's going to be 5 grams per centimeter cubed. All right, so this is the work's not tricky. It's just knowing how to interpret the density problem. So if we're raising up water, right, make sure you consider the size of the base of the container. If it's in a graduated cylinder, how much it rises is our volume. If it's in some other container, then it's going to be the area of the base of the container times how much the water rose. Now let's do a couple problems with population density. So as a reminder, population density is the number of people over the area of land. In this case, the area of land is the amount of space in the banquet hall of the hotel. So Julia runs a hotel. She wants to hold a party in the banquet hall of her hotel. The hall is 70,000 square feet. So that's the area. She found that she can get people comfortably into the hall in a density of 0.004 people per square foot. Right? So you don't all be crammed in 1 square foot, right? That would be awful, right? So you want to have more, if it's only 0.004 people per square foot, it means each person gets more than just 1 square foot. So here we are given the density. Our units is people per square foot, and we want to find out how many people. Right? So we're looking for what's the population of people we can have at the party in the banquet hall at one time. So we'll use the formula up above. Population density we have, that's 0.004 equals number of people is what we're looking for. And the area is 70,000. Right, so we're just going to multiply both sides by 70,000. That's 0.004. Whoops, sorry. Wrote down the wrong number. We're multiplying both sides by 70,000 by the area. Right, so we can isolate. And really, I should have the units in here. That's me not being good. We'll squeeze them in. So this one here is, oh, it's going to be hard to write that in people per square foot. This is square feet. Right, and we're multiplying by 70,000 square feet. Actually, I can also write it like this, feet squared. And this is people per feet squared, and this is 70,000 feet squared. All right, so the feet squared will cancel. The 70,000 feet squared will cancel. And the number of people will be 70,000 times 0.004. So that means that 280 people can be in the banquet hall at one time. So that's the biggest party she can have. We're going to do one last problem. And it's a problem that they love to put on the formatives and benchmarks. In a classroom, the students produced 30,000 BTUs, British thermal units of heat. Now, unlike students are on the ground, right? But the heat is everywhere. So where students only use the area and the people in the banquet hall only use the floor area, the BTUs, the heat, is going to use the entire room. The interior of the classroom is 30 feet long, 15 feet wide, and 15 feet high in the shape of a rectangular prism. Right? So here's the classroom. Must that mean my classroom with its nice sloping ceilings? Right? So 30 feet long, 15 feet wide, and 15 feet high. Right? And we want to know to the nearest thousandth how many BTUs per cubic foot did they produce. Right? So the density is the BTUs per cubic foot. All right, so now we have to calculate out. So the BTUs here, that's our population, if you will, not the students. Oh, they are the ones making the BTUs. And then the feet cubed there, that's the volume. So this is, we're looking at technically population density. It's just our population is BTUs. All right, so now first of all, let's find the volume, because that's easy enough to do. We have the room right here. So the volume of the room is the area of the base times the height of the room. And of course, the area of the base is the floor space down here. Right? So the area of the base is 30 times 15, which is 450 feet squared. The height of the room is 15 feet. Right? And so that makes the volume of the room equal to 450 times 15. So the volume of the room is 6,750 feet cubed. All right, so there we have one measurement that we need. Now we need the population, which is the BTUs. So it says the students produced 30,000 BTUs. So your population, I'll write it in green here, population, doesn't matter how many students were, altogether they produced 30,000 BTUs. So that's the population. So to find the density, we're going to take the population, which is the BTUs, and divide it by the volume of the room, which is 6,750, and I should put the units of measure. You always want to put your units of measure, not even just at the end, but all the way through, and that way you won't have to worry about forgetting them. All right, so now if we simplify, we get, plug into a calculator, 4.4, said thousands, so that's the tenths place, that's the hundredths place, that's the thousandths place, and guess what the 10,000ths place was? It was another 4. All right, so I said to the nearest thousand, so that would reduce down to 4.444, and that is BTUs per foot cubed, or cubic feet. All right, so there is, and I'll just put equals. There we go. So that's our last problem, and that ends density. So I hope you learned a great way to apply what you've learned in volume to finding density and population density. Thanks for watching. Bye for now.